This is a video to talk about the physics of balloons. You can see what we're going to go over today, all as one big file. But let's zoom way in here. Balloons are going to be in equilibrium in that the forces applied up are going to be equal to the forces that are applied down. So basically they're going to move with constant velocity, and the forces that are basically being put on the balloons are the buoyancy force here, the gravitational force, and the drag force. The buoyancy force is lifting the balloon up, while gravity is pulling it down, and the drag force acts in the direction opposite of the velocity, and the velocity is up, and so the drag force pulls it down. All right, let's go through each of these forces one by one. We'll go through the easiest one first, which is gravity. So gravity is relatively straightforward because it's just the mass times gravity. Gravity is 9.8 meters per second squared, and mass is the mass of everything, including the mass of the balloon, the mass of the parachute, and the mass of each of the payloads, or the science packages. So the balloon, the parachute, and the science packages. All right, so there is an FAA regulation in the United States that the mass of the parachute plus the mass of the science payloads has to be less than 12 pounds, which is 5.45 kilograms. So that's the maximum that you really can lift, except for in the case of like if you ask them for a waiver. The next thing to look at starts getting a little more complicated. You can see that it's sort of complicated here, and that's the buoyancy force. The buoyancy force is basically the amount of force that the balloon is pulling up on, and that is equal to the mass of the atmosphere or the air that you've displaced minus the mass of the helium that is displacing that air times gravity. Gravity is 9.8. Mass of the helium, mass of the air. Okay, so the mass of the helium is equal to the number of molecules of helium, which comes from the tanks of helium, and atomic mass of helium, which is 4, times the atomic mass unit. And the atomic mass unit is 1.67 times 10 to the minus 27 kilograms. The hard part is actually finding the number of molecules of helium. And that's basically like you take a tank of helium and then you unload all of that actually into the balloon. And the question is, how many numbers or molecule atoms of helium are there in a tank of helium? That's the real question. So we're going to use the ideal gas law here. The ideal gas law is PV equals NKT. P is the pressure in the tank. V is the volume of the tank. N is the number of molecules of helium, which is the number that we want. K is Boltzmann's constant, which is 1.38 times 10 to the minus 23rd. And then T is the temperature, and it's usually the room temperature. It's the temperature which you basically are putting the helium in. So you rearrange this equation and you get N is equal to PV over N or KT. And then the question is, what is P, what is V? And you have to look up online and see what a tank of helium actually looks like. We usually buy K-size tanks. And if you look on Wikipedia for a K-size tank, you'll see that the pressure is about 2,100 pounds per square foot. That's actually what we have experienced when we're out in the field and we put in a regulator and we start moving the helium out of the tank. We get 2,100 pounds per square foot, which is equal to 1.45 times 10 to the 7th pascals. And then the volume of a K-size tank is about almost 50 liters, which is 0.0499 meters squared. Okay, so given those numbers, N is equal to PV divided by KT. We can do all that math, and we get that N is equal to 1.78 times 10 to the 26 atoms per tank. All right. Now, if we assume that the number of molecules of air is equal to the number of molecules of helium, so basically we have displaced the same number of molecules of air as we have the number of atoms of helium, then we can say that the mass of the air is equal to N times 29 times AMU. And the question is, where does this 29 come from? Well, we can do a little bit of a math here. And we know that air around us is about 78% N2, which is 28 AMUs, and about 22% O2, which is 32 AMUs. We do some math there, and we come up with about 29 AMU. So air is about 29 AMU. That's what the average mass is. Okay, so then the buoyancy force is going to be equal to the mass of the air minus the mass of helium times g, gravity. This is the number of molecules of helium or air. 29 is the mass of the air minus the number of molecules of hydrogen or helium times 4 times AMU times g. You do that math here, and you can pull the N out, you can pull the AMU and the G out, and you can 29 minus 4 is equal to 25. You do this math, and you come up with the buoyancy force is equal to the number of tanks of helium times 72.8 newtons. All right, so if we put in 1 tank of helium, then we have a lift force of 72.8 newtons. If we put in 2 tanks, then we double that. That's very easy. And that's actually the entire way up. The buoyancy force is going to be 72.8 newtons because the number of helium atoms doesn't change as it goes up through the air. Okay, so then if we wanted to just say, like, what is the minimum number of tanks of heliums we have to put in to the balloon to just have it sit there, make it neutrally buoyant? Like, it's not going to lift off the ground, it's just going to sit there. All right? Number of tanks times 72.8, which is the buoyancy force, is equal to the mass of everything times 9.8. You do some rearranging, and the number of tanks is equal to 0.315 times the mass of everything. All right, so you can assume something like 12 pounds is the mass of everything minus the mass of the balloon. And so you add the mass of the balloon, which is 1 kilogram, and you come up with the mass of everything is 6.45 kilograms. That's the maximum that you can really do in the United States without calling the FAA. So then the number of tanks of helium that you need to just have it be neutrally buoyant in this case with a 1 kilogram balloon is about 1 tank of helium. If you put in roughly 1 tank of helium, it will just sit there. 0.87 tanks of helium. If you put in a little bit more helium, it will start to rise. Now, what velocity will it rise at? Well, this is actually now getting into hard stuff. The rest of it was relatively straightforward. Now we get into some harder stuff that has to do with the atmosphere. All right, so the drag force, which is how we can determine the velocity, the drag force is equal to 1/2 the area of the balloon times the drag coefficient times the mass density of the atmosphere times the velocity of the balloon squared. This is the vertical velocity of the balloon. Okay, so how do these things vary? Well, so drag coefficient is constant. It is 0.5 for a sphere. We assume that the balloon is a sphere. That's not really true, but it's close enough. Rho is the mass density of the atmosphere. On the surface, it's 1.29 kilograms per meter cubed, but it changes pretty dramatically as you go up. The projected area of the balloon also changes as you go up because the balloon becomes bigger and bigger and bigger. If we look at how rho changes as a function of altitude, then we have this equation. Basically, the density changes exponentially as you go to higher and higher altitudes. So rho is equal to rho naught e to the minus delta z, the change in altitude, divided by the scale height. And the scale height is equal to kt over mg. K is the Boltzmann's constant again. T is the local temperature. MA is the mass of air, which we actually calculated. It's 29 AMU, which is 4.79 times 10 to the minus 26 kilograms. G is gravity. And so at the surface, you can calculate that the scale height, you plug in all of these numbers here, and you come up with 8.61 kilometers. In 8.61 kilometers, you basically have reduced the density of the air by a factor of 2.7 roughly. One of the problems is that the temperature actually is not constant in the atmosphere. This scale height actually is altitude dependent because the temperature is altitude dependent. I made up like a little temperature profile of the atmosphere, and roughly in the first 8 kilometers roughly of the atmosphere, the temperature falls off at about 10 degrees C per kilometer. Then it stays constant for a little while, and then it starts to rise, and it rises at a lower rate than it was decreasing. So I just put it as 2.5 degrees per kilometer. We're going to make an Excel spreadsheet and actually do all this stuff. And so you'll see that in the next video, actually. So that helps you describe how the rho, the mass density, changes as a function of altitude. You could do it analytically, but we're going to do it on a spreadsheet. So the area of the balloon changes as a function of altitude also. So at the surface, the area looks like this. It has some radius here, and then as you go up, the radius increases because the pressure, the outside pressure, decreases. We're going to describe that by using the ideal gas law again. The ideal gas law is PV equals NKT. T is the local temperature, K is Boltzmann's constant, N is the number of atoms of helium, which we already have, V is the volume of the balloon, which is what we want, and P is the local pressure. The local pressure actually changes exactly the same as the mass density. P is equal to P naught E to the minus delta Z over H, which we'll go over in the Excel spreadsheet. So the volume is equal to NKT over pressure. The volume of a sphere is also equal to 4/3 pi r cubed. And r cubed, or r, is the radius of the balloon, which is useful because the area of the balloon is pi r squared. That is the projected area. Okay, so n in this equation up here, this equation, n is fixed, k is fixed obviously, t is a function of z, p is a function of z. So what we're going to do is we're going to find the volume. From the volume, we're going to derive r. From r, we're going to derive the area. And then we're going to use that area here in the drag equation. So the area, or the drag equation, we have, remember that we're having the buoyancy force is equal to the gravity force plus the drag force. And so the drag force is equal to the buoyancy force minus the gravity force, which is equal to the number of tanks of helium times 72.8 minus the mass of everything times gravity. Now, if you solve for the velocity now, this is the velocity, that's equal to this equation here. So with this equation, we can solve for the velocity of the balloon. And we have that the velocity of the balloon is dependent on the tanks of helium that we've put in, the mass of everything, gravity obviously, the area of the balloon, the drag coefficient of the balloon, and the mass density of the atmosphere. Okay, descent. Once it goes up, the balloon will pop. And actually, you can determine the altitude of the atmosphere at which it will pop by basically looking at the radius here. The point at which the radius becomes too large, the balloon gets stretched too thin, and it pops. And the manufacturer of the balloon actually tells you what that radius is. And so we'll plug that into our formulas in the Excel spreadsheet. Once the balloon pops, we start descending. The descending is much easier because you're just in terminal velocity, where the drag force is equal to the gravitational force. And so we still have the drag force here, which is exactly the same as before, except for a few things are slightly different. The drag coefficient is now 1.5 because that's the drag coefficient of a parachute. The area is the area of the parachute, which I'll go over in a minute. The mass of everything now doesn't include the balloon because the balloon shredded. You can just use this formula to give you the velocity. Now, the velocity actually starts out very large up here at the highest because the air is very thin, so it's falling and the parachute doesn't do very much good. And then as it comes down, it slows down more and more and more and more and more because it's going into thicker and thicker and thicker air. So the area of the parachute is sort of tricky. I sort of messed this up in my code because what happens is when they send you a parachute, they tell you the size of the parachute. Parachute's like 6 feet. And that is when you lay it down, it is 6 feet from end to end. But a parachute isn't like that. A parachute is actually curved like this. And so actually you have that 2 pi r, the radius of the parachute when it's deployed, is equal to 2 times s, because that goes around and makes a circle. And so the radius then is equal to s over pi. All right, s is the size. That's when they tell you it's like 6 feet, then that is the size of the parachute, 6 feet. So the radius is going to be 6 feet divided by pi, or like 2 feet roughly. So the area then is going to be equal to s squared over pi. All right, that's a relatively simple formula. And then rho is the mass density, as it was down here. And it has the same height profile, it's just coming down instead of going up. So then what you can do is you can plug all this stuff into a code, and you can derive all sorts of stuff. We're going to go over that in the next video. The ascending velocity, the descending velocity, the time it takes to go up, where it pops, all of this stuff. You can derive all that. We'll go through that on the Excel spreadsheet. But then I wanted to talk about the horizontal motion of the balloon too. So as the balloon ascends through the atmosphere here, it's actually experiencing different wind speeds. So at the surface, it might be going, say, westward. The wind speed may be westward. And then as it goes up in the atmosphere, it's going to go eastward, and it will experience the jet stream. The jet stream is right here, jet stream. And it's very fast. It can be up to like 100 miles an hour. Then eventually it gets above the jet stream, and the wind speeds are slow once again, at like 10 miles an hour, and they're in the opposite direction. As the balloon is going in, say, Michigan, the balloon launches and it goes a little bit westward, and then it gets above that westward flow, and then it goes eastward, and it accelerates, and then it gets above that jet stream, and then it starts going westward again. It bursts, it goes westward for a little bit, then it gets into the jet stream as it's coming down, and then it gets out of the jet stream and it starts going westward again, and then it lands. Okay, so that's the trajectory that a balloon will take. And we have flight prediction software that will actually go through all of this. But first we're going to go through an Excel spreadsheet on how to actually calculate all of these terms. That's in the next video.